Nova is going to say science. Science means science.
Okay, let's get started with class for today. So this is last bit of content that we're going to cover in this class. Yeah, so the only things left is I'm going to talk a little bit more about linear transformation. I thought I was kind of silly on Monday for like moving things online, but then I think the alarm went off at 12:15. But then in the middle of class, so that's actually a pretty good call, I think. Is there on a task out here? I'm not really playing with this guy right now. I think it's done. So I talked a little bit about linear transformations in the video that I released. There's only one, or I don't remember. There's only a couple of things you need to know about them, mainly like the definition. And then today we're going to look at like how you assign a matrix to a linear transformation. I think I did one example in the video I released on Monday. Does anyone else need the notes at all? Oh. Oh. Very good. Yeah, so there's only a couple of things left. I think there's just a couple of pages pretty much. And so we're looking at, or I guess before I say that, I posted the exam review on Canvas, so you should be able to find that. The exam itself, the final exam, it's worth as much as any of the midterms. I don't remember if I said this in the video or not. So I don't plan on making it more than like 8, however many problems the midterms are. It's like 5 or 6 problems or something like that. So it'll be like a 50 to 60 minute exam, but you have like the full 110 minutes to do it. So time shouldn't be a problem on the exam. It's not going to be like cumulative, but you kind of do need to know the material from the other sections, and that I think I said this verbatim already, but like you have to know about like column spaces and null spaces. You have to know how to do like row reduction, eigenvalues, eigenvectors. That stuff's still coming up, just in new contexts pretty much. So you should expect that to show up on the exam. And I think your exam, it's Friday of next week. So it's still like 9 days away. I think it's in the afternoon at 12 o'clock. But yeah, so the last thing, or last 2 things, is going to be looking at linear transformations and then Markov matrices. So what you need to remember about linear transformations is mostly just the definition. So the definition of a linear transformation is really just any sort of function on a vector that satisfies these 2 properties. So the reason it's called a linear transformation is because it's linear in the sense that you can distribute this function over addition. So if you do t of v plus w, it's the same as t of v plus t of w. And then also you can move constants outside of the transformation as well. So that's what it means to be linear. If you did calculus, well, you're in this class, so you did calculus. If you think about like derivatives and integrals, those are linear because they distribute over sums and you can pull constants outside. So those are examples of linear transformations. One of the examples I went through was actually writing the derivative as a matrix, which is like a linear way of approaching the derivative that's different from calculus. I guess it's derived from what you did in calculus, but can represent derivatives as matrices or integrals as matrices once you choose a basis. And then really what these linear transformations are doing is it's translating vectors in your plane. It also can rotate them. It can like squish them or skew them. That's largely what these transformations are doing. So they naturally kind of show up in like computer graphics. I think I did this in the video, but if I have some sort of vector I'm drawing here, when I'm moving the vector around, I'm really just performing a linear transformation, or at least the tablet's performing a linear transformation. If I'm rotating it, it means the program the tablet's using is also performing a linear transformation. If I shrink it, if I skew it in any way, et cetera, et cetera. And so there's kind of a completely different way of understanding linear algebra, really as the study of linear transformations. There's a book called Linear Algebra Done Right, which is doing linear algebra under the perspective of transformations instead of using matrices. And so they don't do anything with respect to determinants or anything like that. They just think in terms of like operators. And so the two theories are kind of equivalent to one another in a way that I outlined in the video. So you can, given a linear transformation, you can always construct a corresponding matrix and vice versa. If I give you a matrix, you can construct a linear transformation. And it really just depends on choosing a basis vector or choosing a basis for your vector space V and a basis for your vector space W, and then just seeing what the transformation does to those basis vectors. Right, so if I have the kth basis vector of V and I apply T to that basis vector, it's going to be expressible as a linear combination of the basis vectors W1 to Wm. And this is what's going to make up your column, is going to be, I was inconsistent with my notation here. It should be these, like coefficients A are going to make up the columns of the matrix corresponding to the transformation. So this is the last example I did in the video that I posted on Monday. So if I gave you this linear, we're going to make use of this, so it's worth recounting. So for this example, we have a vector space V with the following basis elements, and we have a vector space W consisting of these basis elements. And we want to understand a linear transformation that sends V1 to W2, and then it sends V2 and V3 to W1 plus W3. And so to understand the corresponding matrix, you just read off the coefficients of the basis vectors that serve as your output. So V1 is equal to 1 times W2, and then it's like plus 0 times W3 plus 0 times W1. So this output, so V1 just goes to 1 times W2. So we have a 1 for the first column and then 0, 0 elsewhere. And then T of V2 is equal to T of V3 is equal to W1 plus W3. So this is like 1 times W1 plus 1 times W3, and then plus 0 times W2, which gives you this column associated to V2. And then the same for V3 because they have the same output. And so really you can understand the output of, so if I gave you like, if I wanted to know what the output of V1 plus V2 plus V3 is, you could do it in terms of a linear transformation, or you can think about it in terms of matrix multiplication, which is what we already understand from doing an entire semester of linear algebra, I guess. So if you do like A times this vector 1, 1, 1, it gives you the vector 2, 1, 2, which is exactly the coefficients associated to the three basis vectors we have. So you can understand the output either in terms of matrix multiplication here, or in terms of writing things out in terms of transformations. So they're equivalent to one another. And so I wanted to talk a little bit more about this connection. First, I'm going to go through an example, and then there's going to be a general theorem at the bottom that we'll cite. This is really a way for me to be able to sneak in row reduction into the final exam, kind of, which will be nice for you. So for this example, if we're using the same information as the previous example, so T and the basis vectors for V and W are the same. And so there's three questions that it wants you to answer. It says that since T of V2 is equal to T of V3, it wants you to be able to determine what vectors are going to end up being sent to 0 under T. And then what it wants you to do from there is it wants you to relate what these solutions are going to be to the null space of A, right? If we're thinking about this transformation as this matrix multiplication, then if I were to replace this T by like A times V is equal to 0, that's just asking about the null space, right? So we want to connect vectors sent to 0 and then vectors in the null space of A. And so we'll just do this directly. So because we have T of V2 is equal to T of V3, if I subtracted the two vectors, it would be T of V2 minus T of V3 is equal to 0. And because this is a linear transformation, we know that T distributes over addition, which is the same thing as just subtraction. So this is the same thing as having T of V2 minus V3 is equal to 0. So this is one example of a vector that makes it so if you do T of V2 minus V3, it's going to end up giving you the 0 vector. And because these are basis elements, it turns out this is really going to end up generating all possible zeros or all possible vectors that will end up outputting 0. But there's a way of seeing this as well in terms of matrix multiplication. So before we saw that we can represent our linear transformation via the following matrix. So this is the same matrix I had written on the previous page. This is what we did, or I did on the video from Monday. And so if I were to row reduce this matrix, you can row reduce it to look something like this. So I'm going to make it so this row shows up first, and then I'm going to use this row to get rid of this row. Right? These rows are dependent with one another, so they're going to cancel out. So you could row reduce this matrix into something that looks like the following. And then you can do exactly what we did before. So we have two pivots. This is X, this is Y, and then this is corresponding to Z. And so if I wanted to find the null space of this thing, our free variable is given by Z. And so again, maybe this is like review a little bit, but if I wanted to find the null space, the first column is telling us we have X is equal to 0. Not the first column. The first row is telling us we have X is equal to 0. We have Y plus Z is equal to 0, which implies that we have Y is equal to minus Z. And then we also have like Z is equal to Z. And so you do this thing where you write out like X, Y, and Z, which you can then write as being equal to 0, because X is equal to 0. If I'm writing things in terms of Z here, this is going to be minus 1, and then this will be 1, and then you multiply by Z. And so the main point, so maybe it's been a while since we've done this. I mean, you have to do this with eigenvectors, but this is the null space. Well, we have a notation. I'm not going to write the whole thing. So this is the null space of A. Maybe I should use the word basis. So this is a basis for the null space of A. And so what you'll recognize, and I guess you can switch the sign a little bit because it's a little bit backwards. But if I multiplied this by minus 1, this would become a 1 and this would be a minus 1, which ends up matching with like V2 minus V3. And if you multiply this by minus 1, I mean, this is still going to be 0, right? So these, like what you have here, you can rearrange it so that way it ends up giving you the coefficients for like V2 minus V3, right? So you have a 1 and you have a minus 1 like we have here. So in understanding the null space of A, you really understand what's being sent to 0 under the corresponding linear transformation. And so I guess there's one other part. It wants you to find all solutions to T of V is equal to W2. So it tells you already that we have that V1 ends up being sent to W2. So we know like T of V1 ends up being equal to W2. But we also know what the null space is going to look like as well. So we can say something along the lines of, we have something like T of V1 plus K, where K is going to be equal to like V2 minus V3. Right, if I were to apply this linear transformation to what I have written here, this would be equal to T of V1 plus K times T applied to V2 minus V3. We know this part is going to go to 0 from what I have written up here. And so this will just be equal to T of V1, which is equal to W2 based on how we define the linear transformation in the first place. Right, so using the basis for the null space, we can determine every single vector that's going to end up mapping to W2. Really by taking V1 and then just adding to it any scalar multiple of an element in the null space. It's kind of like what we were doing with the complete solutions in chapter 3, right? It's really the exact same thing, just written in terms of linear transformations now. So it's not really a new idea. Right, so this is one way in which the linear transformation relates to the null space, right? This is like sending the 0 vector, which is akin to just finding a basis for the null space. Any questions about the first part? Okay, yeah, and so if you remember principles of mathematics, there's this notion of a one-to-one map or like an onto map. And so this question of like whether or not we have a vector or like a non-zero vector that sets or ends up being sent to zero is really what it means to have something that's one-to-one. So if the only vector that's sent to zero is the zero vector itself, that means your function's one-to-one. That's what's written down here. So if we have that T is a map from Rn to Rm, we say that the transformation T is one-to-one if the only, or if and only if the equation T of x is equal to zero only has the trivial equation x is equal to zero. So this would be an example of a function that's not one-to-one because we showed that v2 minus v3 ends up being equal to zero. And now we've shown that there's a way of directly relating this to the null space. So what this example really demonstrates, as I'm looking at the entire page pretty much now, is this part right here. So it's a theorem at the bottom. If we have T is a map from Rn to Rm, if it's a linear transformation and we let A be the matrix of T, then T is one-to-one if and only if the columns of A are going to be linearly independent. So in other words, this is the same as saying the null space of A is equal to the zero vector. Right? So if the null space is equal to zero, it means your function's one-to-one. And if it's not equal to zero, it means your function's not one-to-one. That's what this example is really demonstrating, right? This was sent to zero, so you can see the linear, or like the maps, the columns aren't linearly independent, right? We didn't have 3 pivot columns. So I was kind of jumping all over the place, but any questions about the first part at all? Okay. And so the second part is kind of talking about this idea of what it means to have an onto function, which is also a thing from Principles of Math. And so what it means for a function to be onto is that for each b in the codomain, there exists an x in the domain such that t of x ends up being equal to b. And I don't know, I kind of rushed writing this out. So this part here should actually be here. This is not one-to-one. This is what it means to be onto. So this is saying that each b in the codomain is the image of at most one x. Oh wait, no, this part is, don't listen to me. It's the end of the semester. I'm a little bit tired. I'm gonna make mistakes. This is fine. I missed the word at most one. So that's kind of like what it means to be one-to-one. So onto is just saying like if you have anything in the codomain, there's something in the domain that maps to it, right? So you can always express something in the codomain as t evaluated at some vector. So hopefully, I mean, if you took Principles of Math, which is a prerequisite for this class, these ideas should be pretty familiar. Or if you did discrete math as well, you talked about it a little bit as well. And so we want to think about like how the matrix of A relates to a function that's going to be onto. Like how do you determine a function's onto based on the matrix that it has? And so it ends up being this point right here. So T maps Rn onto Rm if and only if the columns of A end up spanning R to the mth power, or like Rm. So this is, we'll see another example that will demonstrate this a little bit better. But let's go back up to the original. So for part 2, it wants you to find a vector that's not in the column space of A. And then it wants you to find a combination of W's that's also not going to be in the range of the transformation. So these should be equivalent questions to one another. And so maybe I'll ask you, there's kind of like a pretty straightforward vector, like one that's maybe a little bit easier to see that's not going to be in the column space. Does anyone see a vector that's not in the column space of A? So we'll look at the vectors 0, 1, 0, and then 1, 0, 1. Is there a vector that can be expressed as a linear combination of these two vectors? Does anyone see or have an idea? And there's like a lot, but yeah, go ahead. Oh, yeah, 1, 1, 0 would be one, right? Because you can't really get rid of, like once you have these two, yeah, you can't really get rid of this guy right here, right? So for instance, you can't really get, so this is part 2. So you can't really get a vector of the following form, like 1, 1, 0. And I'm going to use informal language, but I'll say like out of, and by out of, I mean like as a linear combination of like 1, 0, 0, or sorry, 1, 0, 1, and 0, 1, 0, like so. Because in order to get like the 1, 1 to show up first, you would have to make use of this term, and there's not really a way of getting rid of it via subtraction. Another one would just be the vector 1, 0, 0 as well. I mean, there's a lot that aren't going to be expressible in this way. And so you can also note, so analogously, what this is saying is like if 1, 1, 0 is not in the column space of these two columns here, what this also means is that you can't express like W1 plus W2 in the image of the transformation. So you can also say something like W1 plus W2 is not in the range of T for the exact same reasons, right? Because in order to get W1 and W2, you have to make use of T of V1 and T of V2. But once you make use of those two things, you're getting a W3 involved. And you can't really get rid of it without incorporating more like V2s and V3s, which is going to mess up the term that you have associated with W1. So it's kind of the same reasoning. Like if I can't get this vector in the column space, it means I can't get W1 plus W2 in the range of T. And there are other vectors you can make use of here, like 1, 0, 0 is another one. Any questions about 2? Yeah, and so what I was getting at before is this implies that T is not an onto function, right? If you can't express W1 plus W2 as like an element in the range or like in the output set of T, then that means it's not going to be onto. So this means T is not onto. And then the last part, it wants you to find the rank of A. And it wants you to compare the rank of A, your matrix, to something regarding the linear transformation that we have. And so the rank of A we already talked about before. So the rank of A is just equal to 2 because we row reduced and we had 2 pivots. So the rank of A is equal to 2. And so we want to be able to say something about T. Like what does this number 2 say about T? Does anyone have an idea? So if the rank of A is equal to 2, what does that mean about T? And don't think in terms of it being like 1-to-1 or onto or something like that. Just in terms of like what's going on with T that relates to the number 2. Any ideas? Yeah, it's kind of like a principle of a math question a little bit. But when I'm outputting T or when I'm using T, I'm really sending one vector space to another vector space, but we're not hitting all of W, right? So like what this is going to be equal to, like this 2 is really going to be equal to the dimension of the range of T. So it's the dimension of the output set. I'm assuming most people remember what the word range means, but maybe use a different one. But this is kind of like the output set, is how to think about it. Because we're not hitting all of W under T, we're only hitting a subspace of elements inside of W. And so the possibilities we have is we can have something that's like 0-dimensional, 1-dimensional, 2-dimensional, or 3-dimensional. You can't, like, if you're mapping to W, you can't have something like larger than W. And so we end up finding that the dimension of the output set under T is just going to end up being equal to 2. And it ends up just being equal to the rank that we have. So you should be thinking like the span of the column space corresponds to the range of your transformation, just from construction pretty much. Okay. Any questions about this example at all? Okay. So I kind of talked about this theorem at the bottom of the page a little bit, but again, this is something that's going to show up in true or false questions. I discussed a little bit this idea of having like an invertible matrix theorem, where we now have like, without exaggeration, maybe like 15 ways of determining whether or not a matrix is going to be invertible based on its like rank, the number of pivots, like it's column space, it's null space, et cetera, et cetera. This gives you another way of thinking about it in terms of a linear transformation. So if you have a linear transformation from Rn to Rm, and you let A be its standard matrix, then you can say that the transformation is onto if and only if the columns of A span Rm. So that's like saying you always have a solution for your set of linear equations. This will make more sense on the next page. And then we have that T is 1-to-1 if and only if the columns of A are linearly independent, meaning that you have a trivial null space, right? So you row reduce, you can take your transformation, write out the matrix, row reduce it, and determine like the dimension of your null space, just like we've done in the past. And that'll give you information about whether or not the outputs of T are going to be unique from one another. And so another kind of problem that could show up on the exam, or there could be like a kind of more general version of this problem that can show up like in a true or false. And so on the exam review, I think there's a problem that's kind of like this. So I can give you a linear transformation. This time we're taking some vector space has two vectors or two basis vectors, x1 and x2. And we're sending it to something that's going to be three-dimensional from the fact that we have three components here. So you should be thinking this is kind of like we have one component, this is V1, another component, this is like a V2, and another component, this is like our V3. So this is living in R3. So we're sending something in R2 into something that's going to be in R3. And so what it wants you to do is it wants you to show that T is a 1-to-1 linear transformation. And then it wants you to know if T maps R2. Wait, let me erase this. It wants you to know if T maps R2 onto R3. So maybe this seems a little bit new, but this is really just going to be a row reduction problem. So this is really what we were doing, I think in like chapter 3 or I think it was chapter 3 when we did this. Like it's really just asking you to find the null space and then make observations about the kinds of solutions that you have. So I'll say a little bit more about this. So first, what we want to do, really the only new step is going to be taking T and expressing it as a matrix. I mean, you can do things without thinking about matrices, but we're not going to do it that way because we already know a lot about matrices. So we're going to write things out in the following way. So we're going to write, I kind of already said this already. So V1 is equal to 3x1 plus x2. We have V2 is equal to 5x1 plus 7x2. And then V3 is going to be equal to x1 plus 3 of x2. And so in terms of what this matrix is going to look like, so we're going to think about the corresponding matrix. It's going to look something like this. So the columns correspond to your inputs. This is like x1 and x2. The outputs correspond to your outputs, which is going to be like this. The vectors I'm labeling as V1, V2, and V3. So I've been thinking about things in terms of columns. You can also think about things in rows, in terms of rows as well. And now we know that V1 is equal to 3x1 plus x2. So you can take these coefficients and you can use them to fill out what the rows are going to look like. So like the 3 here shows up here. The 1 times x2 shows up here. So it's kind of like saying V1 is equal to 3 times x1 plus 1 times x2. And then you can also do like 5 times x1, 7 times x2, which will give you 5, 7. And then this one is going to be 1 times x1 plus 3 times x2. So that's one way of thinking about it. You can also think we have 3 times x1, 5 times x1, and then 1 times x1 gives you these numbers right here. And then 1 times x2 plus 7 times x2 plus 3 times x2 gives you these numbers. So it's like the weights that you have corresponding to these vectors that we have here. And so based on this theorem we have here, we can determine information about the linear transformation just by understanding the null space of this matrix and the span of the column vectors as well. And so this is really just a row reduction problem. And just for old time's sake, I think this is like, maybe on the final exam review, I'll have to do a row reduction, but this might be like the last one we do in class. So I'm just gonna go through it anyways by hand. Just for old time's sake, I guess. So this is 3. So I'm switching like the first row and the third row to make it like this. You like having the 1 in front in the first row. And so you can use this row to get rid of the 5 here and the 3 here via various linear combinations of the row. So you have 1, 3. You do minus 5 times this plus this. We'll make it so it's like minus 5 plus 5 will be 0. And that'll be minus 15 plus 7, which will be equal to minus 8. And then minus 3 times this row added to this will give you 0. And then it'll be minus 3 times 3 plus 1 will give you a minus 8. And so then these two rows are equal to one another. So you can use this row to get rid of this row. And so, and then you can multiply this by minus 1 over 8. So you end up getting the following row, reduced row echelon form. Well, it's actually not in reduced row echelon form because I'm keeping the 3. But you could get rid of the 3 here if you wanted to. It doesn't really make a difference. And so in row reducing, what we found is that every single column is a pivot column. So we don't have a null space or we don't have any free variables. And so we can say the following, right? So as the columns are independent, what this means is we know that the null space of A is equal to the 0 vector, right? I always did this before. So this is like, we have 2 pivots, we have 2 columns. That means we don't have any free variables, which means we have a trivial null space. And so this is the same as saying that T is going to be 1 to 1, which I write as this. So this is like 1, 2, 1. It's not uncommon for people to write it in that way, right? So when I'm asking about like 1 to 1 and onto for a linear transformation, I'm really just asking you to do a row reduction problem and then make an analysis on the null space and the column space pretty much, just like we were doing in chapter 3. So I can ask something like this on the final and you can be happy there's like a row reduction problem or something like that. And then the other part, it asks, does T end up mapping R2 onto R3? I guess this is even before doing any sort of calculations. Does anyone know what the answer to this is going to be? I mean, I kind of already did the row reduction, but any ideas? Yeah, sure, Mason. Okay, the answer is going to be no here. I mean, it is kind of like it wouldn't really make sense in the sense that, like, we have something here that's 2-dimensional, and we have something here that's going to be 3-dimensional. You can't use 2 vectors to span like the entirety of R3. Right. So like from that alone, like kind of what you can use as a cheat, and I think there's a true or false question like this on the exam review. But if this number is smaller than this number, then this is never going to be onto, right? They can't take 2 vectors and then use those 2 vectors to span something that's 3-dimensional. If I instead had this as being like a 1,000,000 dimensional, it would be even more absurd where it's like they use 2 vectors to span like something that's 1,000,000 dimensional. Like, it wouldn't really make sense. But another way of thinking about it, and this goes back to something we were thinking about before, is when we're thinking about something being onto, it means there's always a solution, which means that I should be able, if this were onto, no matter what vector I try and solve for, I should end up getting a solution here. But there are going to be scenarios where we don't have a solution. So it kind of goes back to this analysis we had before, where if I have something of the form of like 1, 3, 0, 1, 0, 0, and I were trying to solve for some vector, maybe of the form of like 5, 7, 2, or something like that, we would have this row at the bottom, which would be no solution, right? Because we have 0 plus 0 is equal to 2, that means we have no solution. And so this would mean that T is not going to be onto. So it really goes back to thinking back to the sort of analysis we did in chapter 3, where it was kind of like thinking about full column rank and full row rank. So we have full column rank for this problem, which means that if a solution does exist, it's going to be a unique solution, which means it's 1 to 1. But we don't always have a solution because it doesn't have full row rank. Because it's not full row rank, there are going to be scenarios where we don't have a solution, which means that T is not going to be onto. And another way of phrasing that is just saying, like the columns of A don't span all of R3. In this case, M is equal to 3. So it's another way of thinking about it that is kind of leaning into things that we talked about before in chapter 3. Yeah.
So all the solutions would just be within R2. Right?
Yeah, that's right. Or I mean, well, it's kind of like they could it's gonna be two-dimensional. Like you can span it using two vectors. Yep. So like it's really saying like it's kind of what we were saying here, except it's a different problem, I guess, in that like the dimension of the range of T is going to make up a two-dimensional subspace of R3. You're not going to be able to span something that's three-dimensional using just these two vectors. Yeah, other questions? Okay. This next one, we have time to go through it. I'm probably not going to do a quiz on Friday. I don't know if that's disappointing or good. I don't know how people feel about the quizzes in general. Because there's like, I do want to go through Markov matrices, and eventually I wanted to go into like an application. I kind of wish I interspersed more applications throughout the semester, but there's something called like the $25 billion eigenvector I want to talk about. So I do want to kind of skip the quiz that we usually would have on Friday, so that way I can talk about that. So I think I should have enough time to go through this. Next example. So there's kind of a different way of thinking about eigenvalues and eigenvectors in terms of linear transformations. I'm not going to touch on it for too long. But like when we were thinking about eigenvectors and eigenvalues in the past, that means we had something of the following form, where if you do A times this eigenvector V, it's equal to lambda times the eigenvector V. And so in terms of linear transformations, again, the connection between linear transformation and linear transformations and matrices is that matrix multiplication can be expressed as like T evaluated at some vector. So this can be rewritten as like T of V is equal to lambda V is kind of the idea. And so without using matrices, you could think about eigenvalues and eigenvectors in terms of linear transformations, and they're equivalent to one another. So that's kind of the perspective here. So without writing the matrix A, it wants you to find the eigenvalues of A and describe the eigenvectors for the 2x2 matrix that reflects points across some line through the origin in R2. And so this one is a little bit more visual, I would say. And so we're kind of like in this scenario here. So I'm going to draw some line in R2 that goes through the origin. The direction of the line doesn't really matter at all. Right? Say we have some basic line like this. And so what the transformation is doing, or like what the matrix multiplication is doing, again, they're kind of equivalent notions, is it's going to be reflecting points across some line through the origin. So it's reflecting points or vectors here over like this line in the following way. And so we want to think about eigenvalues and eigenvectors. And when you're thinking about eigenvalues and eigenvectors, you want to be thinking about kind of like how things are preserved, or like what things are going to be fixed, or at least like what behaviors are going to be easy to classify. And so I'm going to tell you, I mean, it's a 2x2 matrix, so we should only have two eigenvectors. And we need to determine like what vectors are going to give us these eigenvectors and then what their eigenvalues are going to be. Does anyone have an idea? So I think there's one that's easier than the other to figure out. Does anyone have an idea of at least one sort of eigenvector that we can have for this example? So maybe one is you can think about being on the line itself. Like if you have a vector like so I'm going to draw it in green. So we have a vector here that's just on the line. pointing in this direction. So I'm going to call this V1. If it's on the line and you apply the reflection of V1, so it like flips across the line, the fact that it's already on the line means that you're not going to be doing anything to this vector V1 through the transformation. So what you would end up finding is that you have V1 ends up having the following. So it ends up being T of V1 ends up just being equal to V1 over again because it's already on the line. So you can't really like reflect it across the line. And so this is going to be an example of having an eigenvector and then the eigenvalue itself is just equal to 1, right? Because this is just equal or equivalent to having 1 times V1, right? So this is implying that we have an eigenvalue given by 1. And so in general, if I were to write things out, so I have it written down here, so I'm going to copy it down. So this is more general. So if you have vectors lying along the line of reflection, this means that they're going to be fixed. Then they stay fixed. Maybe I don't want to write out that much for this, but they end up staying fixed with eigenvalue equal to 1. Yeah, I mean, I guess that's kind of expressed in this, so maybe I shouldn't have to write out these longer phrases or anything like that. But the main point is if you have a vector on the line, if you apply the reflection, it doesn't change anything. Right, and so there's going to be one other kind of class of vectors that we can look at that's going to have a predictable behavior. And that's going to happen, I'm just going to tell you because I want to talk about Markov matrices instead of this. That's going to happen when you have a vector that's going to be orthogonal to the line. So if you have a vector, say like V2, that's orthogonal to the line, if we then reflect it across the line, it's going to look something like this. So it's still going to be orthogonal to the line, except it's going to be pointing in the opposite direction. So this is going to be minus V2. And so what we're saying is that if you do T of V2, you end up getting minus 1 times V2, which then implies that you have an eigenvalue given by minus 1. Right, so I could write out like a longer phrase like I did here, but the main point is if you have a vector V2 that's orthogonal and you apply the transformation, you get an eigenvector V2 and the eigenvalue is just going to be equal to minus 1. So this holds true for any vector V2 that ends up being orthogonal to the line that we end up having. So you can apply translation to these eigenvectors, it'll still be an eigenvector. Or you can shrink it and it'll still be an eigenvector as well. So this one, it's less important. I'm probably not gonna, I don't remember if I added a problem like this on the exam or not, or the exam review. I haven't written the exam. I'm probably not gonna add a problem like this on the exam. The linear transformation stuff, it's probably gonna be a problem of this nature, I would say. So I don't want it to be like one of the more challenging problems. So there could be like a true or false on a linear transformation problem as well. I don't know yet. I haven't written the exam. Any questions about this example? Yeah, so it's another way of, I mean, it isn't really another way. It's kind of the same way of thinking about eigenvalues and eigenvectors, but we just didn't use matrices pretty much. So the last thing I want to talk about this semester is going to be these Markov matrices. There's like an entire class that you could probably dedicate to like Markov theory and Markov matrices, but I just want to give you the basic idea on what they are and where they show up pretty much. It turns out these were pretty, I mean, they're probably instrumental in a lot of different like companies that involve technology. But in particular, it's what Google utilized in order to make a better search engine than everyone else. So like why they were able to be one of the most influential companies of, I guess like the last 30 years or whatever. And so these Markov matrices, what is a Markov matrix? So it's going to be a matrix that has some pretty strict rules set upon its entries. So we're going to assume our Markov matrices are going to be square matrices. So the rows and the columns, or the number of rows and columns, will always be equal to one another. The entries are always going to be non-negative. And then the sum of each column is going to end up being equal to 1. So kind of the interpretation here is you should interpret the columns of a Markov matrix as being some sort of probability that an event is going to end up occurring. So that's why it means like non-negative. So probabilities are always non-negative. The columns adding to 1, they have to add to 1 because something like has to happen. There has to be some sort of outcome that ends up occurring within the sample space that you have. And so before getting into applications, there's going to be 2 important properties that are held by Markov matrices that we're going to utilize. So the first result is going to tell us Markov matrices are closed under multiplication. And then the second result is going to find an upper bound for the eigenvalues you can have for a Markov matrix. And then we're going to utilize both of these properties in conjunction to one another in order to make a key observation about what Markov matrices end up telling you. And so I'm going to quickly go through this proposition. So this one is telling you that if A and B are Markov matrices, then A times B is going to be a Markov matrix as well. And I'm only going to show this for 2x2 matrices out of the interest. I mean, you could do it for n by n, obviously, but it takes too long. And this isn't really what I'm trying to demonstrate. So I'm just going to do this for 2x2 matrices. So we're going to assume we have 2 Markov matrices, A, B, and then C, D. And then we also have another one given by E, F, and then G, H. So we're assuming that these are Markov matrices. And really the characteristic or the quality that we care about is that if you take A plus C, it has to be equal to 1. If you do B plus D, it's equal to 1. If you do E plus G, it's equal to 1. And if you do F and H, if you add those together, it's going to be equal to 1. And so if I perform the matrix multiplication of these 2 matrices, we have A, B, C, D, then we have E, F, and then G, H. So you end up getting the following. So you end up getting A, E plus B, G, right? So you have like A times E plus B times G. I mean, kind of know we've done matrix multiplication, so maybe I don't have to explain where this is coming from. So this is A times F plus B times H. You have C times E plus D times G, and then this is going to be C, F, and then plus DH. And so what we need to do is we need to show that if I take the sum of this column, it's still going to be equal to 1. And if I take the sum of this column, it's still going to be equal to 1 as well. And so I'll just do it for the first column. The other column, the argument kind of is the exact same. So if I do AE plus BG, and then I do plus CE plus DG, I'm going to combine kind of like terms. So we have this AE and this CE, and we have the EE and we have GG. So I'm going to pair those terms together. So I'm going to move things around, write this as AE plus C times E, and then this is going to be plus BG plus DG, like so. And so what I can do is I could factor out the E from the first term. So this is E, and then you have A plus C, then you have G, and then you have B plus D. And so we have A plus C. A plus C was the sum of the first column here. So we know this is equal to 1 from the fact that it's a Markov matrix. Similarly, we have B plus D. That's the sum of these 2 entries here, which we also know is equal to 1 because it's a Markov matrix. And so this is equal to E plus G. And we know E plus G is equal to 1 because we know this is a Markov matrix as well. So this ends up being equal to 1. Right, and so the same thing is going to hold true if you went with the other column as well. The argument is pretty much the exact same. You just move things around, factor things out. It ends up still being equal to 1. And so if you multiply any 2 Markov matrices, well, I only showed it for 2x2, but the argument kind of extends if you do n by n. What ends up happening is you always have A times B as Markov, which means that if you have a matrix A that's a Markov matrix, you can take powers of that matrix and it's still going to be a Markov matrix, which is really what we're going to care about. All right, so any questions about kind of the idea of the proof here? Okay, so I'm going to stop here, and then Friday there won't be a quiz. I'm just going to continue talking about these Markov matrices. And if I end class early on Friday, then so be it.
Because I